Imagine opening up a diesel engine and seeing no cylinder head, no valves, nothing at the top at all, just two pistons racing toward each other in the same cylinder, smashing air and fuel together before exploding them apart again. It sounds wrong, overcomplicated, like something that should have died in a lab in the 1930s, but it didn't. This engine helped win World War II, outlived its replacements, powered nuclear facilities, and, decades later, is still in service today. So the real question is, why didn't it fail? This is the story of the Fairbanks-Morse opposed-piston diesel, the weirdest diesel engine America ever built. Start in Beloit, Wisconsin. Not exactly a place you'd expect a radical engineering breakthrough. Fairbanks-Morse was a scale company, literally. They made industrial scales, pumps, and basic machinery. By the 1920s, they were building small diesel engines, but nothing revolutionary. Then, in the early 1930s, they came across a strange German idea. A German engineer named Hugo Junkers had started chasing this concept years earlier, back in 1926. Junkers wasn't just some tinkerer. He was already one of the most important aircraft designers alive, the man behind some of the first all-metal airplanes ever built. His obsession was an engine with no cylinder head at all, two pistons per cylinder, facing each other with the combustion happening in the dead center between them. By 1932, that obsession had become real hardware. A line of six-cylinder opposed-piston diesels called the Jumo, built originally to power airships and later heavy aircraft. No valves, no wasted weight at the top of the cylinder. Just raw, efficient compression. It was efficient, compact, and unlike anything most American engineers had worked with. Fairbanks-Morse didn't just copy it, they bought a license to the idea and adapted the concept into something much larger and tougher. By 1933, their engineers were already redesigning it for industrial duty. A year later, the first American opposed-piston prototype was running on a test stand, a six-cylinder unit with a 5x6-inch bore and stroke, small enough to fit on a railcar for field testing. Early versions in the 1930s were rough. Some experimental designs even used chain-driven systems to synchronize the two crankshafts. It worked, but not well enough. Chains stretched, timing drifted, and reliability suffered, so engineers redesigned it. By the late 1930s, they replaced the chain with a gear-driven vertical shaft system, locking both crankshafts together with precision. That same year, 1934, Fairbanks-Morse ran an endurance test on a much bigger version, an 8-cylinder unit, 8 inches by 10 inches, putting out 1,000 horsepower. It ran, and it kept running, and somebody from the US Navy was paying attention. That endurance test became the foundation of the Model 38 engine, the version that would define the design for decades. Here's how it actually works. Each cylinder has two pistons, one coming from the top, one from the bottom. They meet near the center, compressing air and fuel between them. When combustion happens, the explosion forces both pistons apart at the same time. No cylinder head, no valves. Instead, ports are cut into the cylinder walls. As the pistons move, they uncover intake and exhaust ports in a carefully timed sequence. Exhaust opens first, then intake, allowing fresh air to push out spent gases, a process called scavenging. Because it's a two-stroke diesel, it needs forced air, so a blower continuously pushes air through the engine. And starting it, no electric starter. Instead, compressed air is injected directly into the cylinders, forcing the pistons to move until the engine fires on its own. One detail that separated the Fairbanks-Morse version from its German ancestor. In the Junkers Jumo, power was taken off the upper crankshaft. Fairbanks-Morse flipped that, pulling power from the lower crank instead, and used bevel gears on a vertical shaft to keep the two crankshafts locked in perfect time with each other. Small difference on paper, huge difference in how serviceable and how tough the American version turned out to be. It's complex, it's unconventional, but in the right environment, it's incredibly effective. The US Navy noticed early. By the mid-1930s, Fairbanks-Morse engines were being installed in early American submarines. Submarines had one big problem: space. Everything had to be compact, powerful, and reliable. And this engine delivered, mostly. There were design challenges. In some early installations, the engine had to be shortened to fit submarine engine rooms, which made maintenance more difficult, especially for the upper pistons. But once refined, the design proved something critical. It could run reliably in one of the harshest environments imaginable. During World War II, thousands of these engines were built and installed in US submarines and naval vessels. At peak wartime production, they were being produced at an incredible rate, rolling out of the Beloit plant fast enough to keep pace with an entire submarine fleet being built simultaneously across multiple shipyards, and more importantly, They didn't fail. In submarine warfare, reliability isn't convenience, it's survival. A diesel engine that quit at the wrong moment didn't just strand a boat, it could get the whole crew killed. And this engine earned a reputation the hard way, by working, patrol after patrol, through the most intense submarine campaign in American history, the one that helped strangle Japan's supply lines and bring the war in the Pacific to an end.
Naval warfare.
Engineers even pushed the concept further. In early 1940, with war already raging in Europe and the Navy bracing for the possibility of joining it, the service came to Fairbanks-Morse with an unusual request. Build something bigger. Much bigger. 3,000 horsepower from a single engine for the next generation of submarines. A young engineer named Robert Beadle was put in charge of the program, and his team didn't just scale up the existing design, they reimagined it entirely. The result was nicknamed the Diamond Engine. Instead of one cylinder bank and 2 crankshafts, the Diamond used 4 crankshafts, one at each corner of a square layout with 4 full banks of 6 opposed piston cylinders feeding into them, 24 cylinders total, all driving a single output shaft. On paper, it was an engineering marvel, proof that the opposed piston architecture could scale almost indefinitely. In practice, it was complicated, expensive, and arrived too late and too over-engineered to see widespread service. A handful were built and tested. The concept worked. It just wasn't what the fleet actually needed. The main production engine remained the Model 38, refined, proven, and battle-tested. After the war, Fairbanks-Morse tried something ambitious: locomotives. They entered the railroad market in the early to mid-1940s, eventually building well over 1,000 locomotives before they were done. Early cab units called the Erie built, named for the Erie, Pennsylvania plant where they were assembled, were the company's opening shot at the dominant builder of the era, electromotive diesel. On paper, these locomotives were impressive: high horsepower, strong pulling force, and advanced engineering. Not a single Erie-built unit survives today. Everyone was eventually scrapped. But this is where things went wrong. The engine that thrived in submarines struggled on land. Why? Environment. Submarines operate at sea level, with access to unlimited cooling water and steady operating conditions. Locomotives face heat, altitude, dust, and constant changes in load, especially in mountainous regions. Under those conditions, the engine's lower pistons ran hotter than expected. Over time, this led to piston failures and damage to cylinder liners. In extreme cases, failures could become catastrophic. Maintenance didn't help. The opposed piston design was more complex to service than competing engines. Repairs often required significantly more disassembly, making them slower and more difficult. By 1953, Fairbanks-Morse was trying to recover from an earlier locomotive line, the sea liners, which had flopped. Their answer was the H-2466, better known as the Trainmaster, a 2,400 horsepower, 6-axle hood unit built around a 12-cylinder version of the opposed piston engine. At the time, it was one of the most powerful single-engine diesel locomotives anyone had ever built, capable of generating over 112,000 pounds of tractive effort. Railroads that hauled heavy tonnage loved the idea. The Norfolk and Western and the Virginian Railway put trainmasters to work, dragging coal trains through the grades of the Blue Ridge Mountains. The Wabash ran them on hot, high-priority freight. For a moment, it looked like Fairbanks-Morse had finally built something that could go toe-to-toe with EMD. It didn't last. Some railroads decided the Trainmaster simply had more power than they needed or knew what to do with. Others ran straight into the engine's old problems, now amplified by a bigger, more complex 12-cylinder version. The Southern Pacific found that the Trainmaster's air intakes clogged with sand and dirt kicked up from the roadbed. Electrical systems proved troublesome. Cooling water consumption ran higher than competing locomotives. The New Haven Railroad even floated a dual-mode version of the Trainmaster that could switch to third-rail electric power in New York's electrified territory, a clever idea that got canceled, in part because Fairbanks-Morse's reputation was already sliding and because of friction between FM and General Electric, who would have supplied the electrical equipment. The New Haven eventually took the same concept to EMD instead, and that partnership produced the FL9, a locomotive that ran for decades. The idea that should have belonged to Fairbanks-Morse ended up making somebody else famous. And then there was a bigger issue: training. By the 1950s, one company, EMD, dominated the railroad industry. Mechanics were trained on their systems, their tools, their methods, their habits. Fairbanks-Morse engines were different, completely different. But instead of retraining entire workforces, many railroads simply treated them like standard engines and maintained them incorrectly. One historian who studied the company directly, author John Kirkland, put it bluntly: the same opposed-piston engine that ran flawlessly for the Navy in submarines and performed well for railroads that actually trained their people on it properly, turned in poor results elsewhere for one simple reason. It wasn't the machine. It was the men assigned to keep it running and whether anyone had bothered to teach them how. The result? Poor reliability, rising costs, and a reputation the engine didn't fully deserve. In the end, only a little more than 100 trainmasters were ever sold, a rounding error next to EMD's production numbers. By the late 1950s, Fairbanks-Morse exited the locomotive business entirely, officially closing the door in 1959 and turning its full attention back to marine and stationary engines. But here's the key point. The engine didn't fail everywhere. It failed in one specific environment. Put it back in its natural habitat, marine use, and it kept working. It powered destroyer escorts, icebreakers, and Coast Guard cutters. It ran in ships that needed reliability above everything else. And then, in the 1960s, a new role appeared: nuclear power. Nuclear plants require emergency diesel generators, machines that must start instantly and run flawlessly during a power loss. That's exactly what Fairbanks-Morse engines were built to do. Decades of proven reliability made them a natural choice. Variants of this design are still used in nuclear facilities today. Even nuclear submarines didn't replace it entirely. When the US Navy moved to nuclear propulsion, submarines still needed backup diesel engines for port operations, emergency power, and startup systems. Fairbanks-Morse engines continued to serve in that role across multiple submarine classes, not as the main engine anymore, but as the one you trust when everything else fails. And the company? Still there. Fairbanks-Morse Defense continues to build and support engines based on this architecture. Modern partnerships, like the one with Achadi's Power, the same San Diego firm pushing opposed-piston engines back into trucks and other modern applications, are even updating opposed-piston designs for modern efficiency and emissions standards. Nearly a century later, the idea is still alive. So go back to that original question. Why didn't it fail? Because it wasn't a bad design, it was a specialized one. In the wrong environment, with the wrong support, it struggled. But in the right conditions, it did exactly what it was built to do: run reliably no matter what. And that's why, 90 years later, somewhere in a ship, a power plant, or a system you'll never see, this strange, headless double crankshaft diesel engine is still there, waiting, ready to start in seconds, exactly like it was designed to.